Gravity holds galaxies together and keeps your feet on the ground, the one force we think we understand. But shrink down, smaller than an atom, smaller than a proton, and keep falling. At a scale so tiny it makes a single atom look as wide as the whole universe, our best theory of gravity simply breaks. We will plunge into a black hole's heart, watch space itself boil, and reach the edge where time dissolves. If this wonder pulls you in, a quick like and subscribe helps. Prepare yourself. We begin. An apple lets go of a branch and drops into the grass. You have watched something like it 1,000 times. A dropped spoon, a falling leaf, rain sliding down a window. Gravity is the most familiar thing in your whole life. It pins you to your chair right now. It keeps the oceans in their basins and the moon looping around the earth. For most of human history, nobody asked why. Things fell because falling is what things did. Then a young man sat in a garden and watched fruit come loose from a tree, and he asked a strange question. The same pull that dropped the apple, could it reach all the way to the moon? That man was Isaac Newton. His answer changed the world. Every object with mass, he said, tugs on every other object. The earth pulls the apple. The apple pulls the earth back, far too gently to notice. The sun holds the planets. The planets hold their moons. One single rule, written as a short equation, described the fall of an apple and the orbit of a world with the exact same math. It felt like a miracle of tidiness. Sailors used it to cross oceans. Astronomers used it to predict eclipses years ahead. When a wobble appeared in the orbit of Uranus, mathematicians pointed to an empty patch of sky and said a hidden planet must be there. Telescopes turned to that spot, and Neptune was waiting. Gravity had become the most trusted idea in all of science. Here is the comparison that makes Newton's picture easy to hold. Imagine an invisible rope running between every two objects in the universe. The heavier the objects, the thicker the rope, and the harder the pull. The farther apart they drift, the thinner the rope becomes. Stretch that web of ropes across the whole cosmos, and you can predict where every planet will sit tomorrow, next year, a century from now. For more than 200 years, the ropes held. Gravity looked finished, solved, a closed book. Scientists moved on to other puzzles, confident that the falling of things was understood down to the last decimal. They were wrong in a way nobody saw coming. Because Newton had described what gravity does with breathtaking accuracy, he had never explained what gravity actually is. What are those invisible ropes made of? How does the sun reach across 93 million miles of empty space and grab a planet it never touches? Newton himself admitted he had no idea. He called it action at a distance and confessed the mechanism was a mystery he could not solve. That mystery sat quietly in the background for generations. A small crack in a beautiful theory. Most physicists ignored it. The equations worked, so why worry about the philosophy underneath? Then, in a patent office in Switzerland, a clerk with wild hair and no professorship started thinking about light and speed and what happens to space and time when you move very fast. He was about to tear up Newton's tidy picture completely. He would prove that the invisible ropes do not exist at all, and that gravity is something far stranger than a pull. The apple was never really being tugged. It was following the shape of something you cannot see. The clerk was Albert Einstein, and his idea sounds impossible the first time you hear it. Gravity is not a force reaching across space. Gravity is the bending of space itself. Picture a large trampoline pulled tight and flat. Now roll a heavy bowling ball into the middle. The surface sags into a deep dip around the ball. Roll a small marble across that trampoline, and it curves toward the bowling ball, circling the dip, spiraling inward. No rope connects them. The marble simply follows the sloped surface it is rolling on. Einstein said the universe works like that trampoline, only in more dimensions than you can picture. The bowling ball is the sun. The dip is the curve. It presses into space and time together, a single fabric he called space-time. The earth is the marble. rolling along that curve, tracing the dip year after year. The planet is not being pulled by an invisible rope. It is coasting in a straight line through a landscape that has been bent underneath it. This was a wild claim, and Einstein knew he needed proof. His math made a bold prediction. If space really bends around heavy objects, then starlight passing close to the sun should curve as it travels through the dip. The star would appear slightly out of place, shoved sideways in the sky by the warp in space. In 1919, astronomers sailed to remote islands to watch a total eclipse, the only time the sun goes dark enough to see stars right beside it. They measured the star positions. The light had bent by the exact amount Einstein predicted. Newspapers around the world ran the story. A quiet clerk had overthrown Newton, and gravity would never look the same. The new picture explained things Newton never could. Mercury's orbit had a tiny wobble that Newton's ropes got wrong. Einstein's bent space-time got it perfect. Time itself, he showed, runs slower deep inside a gravitational dip. Clocks on the ground tick a hair slower than clocks on a mountain. This sounds like fantasy, yet the satellites guiding the map on your phone correct for it every single second. Ignore Einstein for one day, and your navigation would drift off by miles. So gravity became geometry. Mass tells space how to curve. Curved space tells matter how to move. The two dance together in a loop, and out of that dance falls everything from a dropped apple to the swing of a galaxy. It is one of the most beautiful ideas the human mind has ever produced, and it has passed every test thrown at it for over 100 years. Black holes fell out of the equations. Ripples in space-time called gravitational waves fell out too, and machines finally caught them a century later, humming from two black holes crashing together 1 billion light-years away. Every prediction confirmed. Einstein's theory stands as one of the crown jewels of physics, and yet a shadow hangs over this triumph. Einstein described gravity as a smooth, flowing sheet, a fabric that bends in graceful, continuous curves. His whole theory assumes that space-time is smooth all the way down, endlessly divisible, silky at every scale. But another revolution was brewing at the same time, in the world of the very small, and its rules were the opposite of smooth. They were jagged, jumpy, and utterly bizarre. When that world finally met Einstein's silky fabric, something had to give. While Einstein was bending the heavens, a different group of physicists was staring into the atom, and what they found there made no sense at all. Shrink down to the size of an electron, and the calm, orderly world you know falls apart. Down there, nothing sits still. Nothing holds a fixed position. A particle does not travel along a clean path like a thrown ball. It seems to exist in a smear of possibilities, everywhere at once, until the moment you look. This is the realm of quantum mechanics, and it is the most successful and the most baffling theory ever written. Start with the strangest rule of all. An electron circling an atom is not a tiny planet on a tiny orbit. It is a blur, a cloud of chance, more likely to be here than there, but never truly in one spot. Only when a measurement pins it down does it snap into a single location. Before that instant, asking where it is has no clean answer. Then comes the rule that matters most for our story, the one written by a young physicist named Werner Heisenberg. He proved that you can never know everything about a particle at once. The more precisely you measure where something is, the more wildly uncertain its motion becomes. Pin down its position, and its speed explodes into a fog. This is the uncertainty principle, and it is not a flaw in our instruments. It is baked into reality itself. Here is a comparison that helps. Imagine trying to photograph a hummingbird's wing. Use a fast shutter, and you freeze the wing sharply, but you lose all sense of how fast it beats. Use a slow shutter, and you capture the blur of motion, but now the wing's exact position smears across the frame. In the quantum world, this trade is absolute. Sharpness in one thing forces blur in the other. You can never have both. The consequences get wilder. Empty space, the quantum world says, is never truly empty. Even in a perfect vacuum, particles flicker into existence and vanish again in tiny bursts, borrowing energy for the briefest possible moment before paying it back. Space is not calm and still. At the smallest scales, it fizzes with restless activity, a sea of things popping in and out of being. This theory should be laughed out of the room. It sounds like nonsense. Yet it is the most tested idea in the history of science, correct to more decimal places than almost anything humans have ever measured. Every transistor in the device you are using runs on these rules. Lasers, medical scanners, the glow of the stars, all of it obeys the jittery quantum law. So now stand back and look at the two great theories of the 20th century side by side. Einstein's gravity describes a smooth, graceful, curving fabric of space-time, elegant and continuous. Quantum mechanics describes a frantic, flickering, uncertain world of blurs and jumps and borrowed energy. One is calm, one is chaos. One rules the cosmos of stars and galaxies. One rules the tiny cosmos inside every atom. Both are right. Both have passed every test. The trouble is simple to state and terrifying to face. When you try to make these two perfect theories work together, in the one place where both must apply at once, they do something no successful theory should ever do. They start screaming out answers that cannot possibly be true. Most of the time, the two great theories never meet. And that is exactly why physics has gotten away with the problem for so long. Gravity is astonishingly weak. It only becomes powerful when you pile up enormous amounts of mass, like a planet or a star. So Einstein's smooth space-time matters for big, heavy things across huge distances. Quantum mechanics rules the opposite kingdom, the realm of tiny, light particles at tiny distances, where gravity is so faint it can be ignored entirely. Think of it like two rulers who never share a border. Einstein governs the giant and the far. Quantum mechanics governs the small and the near. A star is too big to care about quantum jitters. An electron is too light to bend space-time in any way you could ever notice. For a century, each theory has ruled its own territory in peace, and physicists could use one and forget the other. Consider how lopsided the weakness of gravity really is. Hold a small magnet over a paperclip on a table. That tiny magnet lifts the clip clean into the air. In that moment, a magnet you could close in your fist beats the gravitational pull of the entire planet Earth, all of its mass tugging the other way. Gravity is that feeble compared to the forces inside atoms. This is why the two theories almost never collide. Almost, because there are places in the universe where something is both incredibly heavy and incredibly small at the same time. Places where a mountain of mass gets crushed into a space narrower than a single particle. In those places, gravity is strong and the quantum jitters are loud, both at once, screaming for attention in the very same spot. And there, the two theories are forced to shake hands. There, physicists must use gravity and quantum mechanics together in one calculation describing one object. This is where the peace treaty collapses. When scientists write down the equations that combine Einstein's smooth spacetime with the jittery quantum world, the math does not give a strange answer or a difficult answer. It gives an impossible one. The numbers blow up. Quantities that should be small and sensible race off toward infinity. Ask how strongly two particles pull on each other through quantum gravity at the tiniest range, and the equation answers with infinity, again and again, in every direction. Infinity is the math telling you it has failed. A theory that predicts infinity is a theory that has stopped describing reality. It is like asking a calculator for the temperature of a room and watching it insist the answer is endless heat with no upper limit. Something in the setup is broken. For decades, the brightest minds in physics have hurled themselves at this wall. Einstein spent the last 30 years of his life chasing a way to unite his gravity with the quantum world, and he died without finding it. Generation after generation of physicists has tried since. The wall still stands. This is the deepest unsolved problem in all of science. Two theories, each flawless in its own home, that cannot live together in the one house where both belong. The crack between them runs straight through the foundation of reality. To find where the crack begins, we have to do something dangerous. We have to zoom in deeper than atoms, deeper than the particles inside them. We have to keep shrinking until we reach the scale where the two theories finally collide head-on, and ask what waits for us at the very bottom of the world. Take any distance and cut it in half. Then cut the half in half. Keep going. Nothing seems to stop you. Slice the width of your hand down to the width of a hair. Slice the hair down to a single cell. Slice the cell down to a molecule, then to a single atom. Keep slicing. Inside the atom, dive past the electron cloud into the nucleus. Split the nucleus into protons and neutrons. Crack a proton open and find quarks whirling inside. And still the question waits, patient and unnerving. Can you keep cutting forever? For thousands of years, thinkers assumed the answer was no. There must be a smallest piece, an uncuttable grain of reality. The ancient Greeks even named it. They called that final grain the atom, from a word meaning that which cannot be divided. They pictured the world as a vast heap of these tiny, solid, unbreakable beads. They were right about the instinct and wrong about the target. The thing we now call the atom split wide open. Then the pieces inside split too. Every time humans built a bigger machine to look closer, the supposed smallest thing revealed a whole zoo of smaller things churning inside it. The bottom kept running away from us. So the question sharpens into something profound. Is space itself endlessly divisible, like a number line you can always chop finer? Or is there a true flaw, a shortest possible length, a distance so small that the word smaller loses all meaning below it? Here is a way to feel the strangeness of both answers. If space can be cut forever, then between any 2 points, no matter how close, there are infinitely many more points, an endless bottomless staircase with no last step. But if space has a smallest unit, then reality is more like a screen made of pixels. Zoom in far enough, and you would hit a grain, a single, indivisible tile of existence, and nothing could ever be located between one tile and the next. Both ideas feel wrong. An endless staircase into nowhere, or a universe secretly built from pixels too small to ever see. One of them has to be true, and physics has spent a century trying to find out which. The reason this matters so much comes straight from the war we just witnessed. Remember, the two great theories only clash when things get both heavy and small at the same time. The smaller you go, the louder the quantum jitters become, and the more violently space-time is supposed to shake. So if you keep cutting distance down and down, you must eventually reach the exact scale where Einstein's smooth fabric and the frantic quantum storm crash into each other with full force. That scale has a name. It is the frontier where all of physics runs out of road, and it sits at a distance so unimaginably tiny that the numbers almost stop meaning anything to a human mind. Scientists calculated exactly how small it is by combining the three deepest constants in nature: the speed of light, the strength of gravity, and the quantum jitter itself. Fold those three numbers together in the right way, and out drops a single length, the shortest distance where our physics still makes any sense at all. Below it, our theories fall silent. And what that length turns out to be will stretch your imagination past its breaking point. The length has a name, borrowed from the physicist who first stumbled onto its ingredients. It is called the Planck length, and it is small in a way your brain was never built to picture. Start with something you think of as tiny, a single atom. An atom is already so small that lining up millions of them side by side would barely cross the width of a human hair. Now go smaller. Inside that atom sits the nucleus, and the nucleus is 100,000 times smaller than the atom around it. Now go smaller still, down to a single proton in that nucleus, one of the tiniest objects we can measure. The Planck length is smaller than a proton by about 100 billion times. That number is so large it slides right off the mind, so let us build it into something you can almost hold. Imagine you could grab a single atom and blow it up, swell it larger and larger until it was as wide as the entire observable universe. Every galaxy, every star, all of it fitting inside one bloated atom. You have magnified that atom by an amount beyond all imagining. On that same monstrous scale, how big would the Planck length become? About the size of a tree? Blow up an atom to the width of the whole cosmos, and the Planck length grows only to something you could stand beside in a garden. That is how far below the atom this distance hides. It is the basement beneath the basement beneath the basement of reality. Why does this particular length matter? Because it is where the two warring theories are destined to meet. The Planck length is stitched together from the three deepest numbers in nature. Take the speed of light, the fastest anything can travel. Take the strength of gravity, the constant in Einstein's equations. Take the quantum jitter, the number that sets the fuzziness of the small world. Combine all three in the only way that produces a length, and this is the answer that falls out. That combination is the whole point. Any distance built from gravity and the quantum world together is a distance where gravity and the quantum world both matter at once. The Planck length is the exact scale where Einstein's smooth spacetime and the frantic quantum storm are forced to occupy the same tiny room. It is the address of the collision, and here is the unsettling part. At that scale, our best theory says something has to break. Zoom down toward the Planck length, and the quantum jitters in space-time grow wilder and wilder. The smooth fabric Einstein described starts to shudder. His equations assume space stays silky no matter how far you zoom. Yet the quantum rules insist that at the Planck length, the fabric should be convulsing violently, tearing at itself, refusing to hold still. So the Planck length is a wall. Above it, physics works. We can describe atoms, stars, galaxies, light, everything. Below it, our theories stop giving sane answers. It may be the shortest distance that even exists, the true pixel of reality, or it may be a curtain we simply cannot see behind. Nobody knows. You might think the fix is obvious. Just build a better microscope, look closer, peer down past the Planck length, and settle the question with your own eyes. But nature has locked that door, and the reason you can never open it is one of the strangest facts in all of physics. You would think that seeing something smaller is just a matter of a better microscope, grind a finer lens, build a stronger machine, look harder. For most of history, that was true. But at the Planck length, this simple plan runs into a wall built by the laws of nature themselves. To understand why, you have to know how looking actually works. When you see anything, light bounces off it and into your eye. The color of that light sets how small a thing you can make out. Ordinary light has waves too broad to resolve something as small as an atom. It is like trying to feel the shape of a grain of sand while wearing thick winter gloves. The gloves are too clumsy to trace the tiny bumps. To see smaller things, you need light with finer waves, waves packed closer together. And here comes the catch that changes everything. Light with finer waves carries more energy. The tighter you squeeze the waves, the more punch each burst of light delivers. To see an atom, you already need high-energy light like X-rays. To see a proton, you need the ferocious beams inside giant particle colliders. There is a strict trade. Smaller targets demand higher energy. Always. Now push that rule to its limit. Suppose you wanted to see something as small as the Planck length. The waves you would need would be so impossibly fine, so violently packed, that the energy they carried would be beyond anything imaginable. You would be firing a bolt of pure energy so concentrated that it would break the very thing you were using to look. Remember Heisenberg's rule from the quantum world. To pin down a smaller and smaller position, you must accept a wilder and wilder blast of energy. The two are locked together forever, position and energy, traded against each other, with no escape. Reaching down to the Planck length means unleashing the Planck energy, and the Planck energy is a monstrous amount of power crammed into a single point smaller than a particle. Picture it like this. To read the finest print in a book, you shine a brighter and brighter light. But suppose that beyond a certain brightness, the light itself set the page on fire. Now, the harder you try to read the tiny letters, the more surely you destroy the very words you were trying to see. That is the trap waiting at the plank length. The act of looking closely enough would wreck the thing you are looking at, and worse, it would wreck the space around it. So the problem is not that our machines are too weak, it is that the universe forbids the measurement in principle. There is no clever workaround, no future technology that slips past the rule, because the rule is written into the deepest laws we know. Any tool sharp enough to probe the Planck length would carry enough energy to warp space-time itself at that spot. And that is where the trap turns from strange to genuinely terrifying. Because when you cram that much energy into that smaller space, something forms. Something that Einstein's own equations predict. Something that does not just block your view, but swallows it, seals it, and hides it forever behind a one-way door. The closer you try to look at the smallest scale, the more surely you build the one object in the universe that no light can ever escape. Here is the fact that stops physicists in their tracks. Try to look closely enough at the Planck length, and you do not see anything smaller. You create a black hole instead. Follow the logic step by step because it is airtight. To probe a tiny distance, you must pour in a huge amount of energy, concentrated into a tiny space. That was the trap from a moment ago. But energy and mass are two faces of the same thing, joined by the most famous equation in science. A blast of concentrated energy behaves exactly like a lump of concentrated mass. And Einstein's gravity gives an iron rule about mass squeezed into a small space. Pack enough of it into a small enough region, and gravity wins. The mass collapses in on itself and forms a black hole. So watch what happens when you try to reach the Planck length. You focus your beam tighter and tighter, pumping in more and more energy to see the smaller and smaller target. As you close in on that scale, the energy piled into that speck of space crosses a threshold. Gravity takes over. The region snaps shut into a tiny black hole, a sphere of no return. Your view is gone. Whatever you were trying to see now sits sealed behind a wall that no light, no signal, no information can ever cross. Physicists call this the generalized uncertainty principle, and it adds a brutal twist to Heisenberg's old rule. In the ordinary quantum world, the harder you push, the sharper your view gets. But once gravity joins the game, that stops being true. Push past the Planck scale, and the view starts getting blurrier again, because your own probing energy is now making black holes that hide the target. You have hit a floor. Below it, sharper looking makes things worse, not better. Picture a diver trying to reach the deepest point of the ocean. The deeper she goes, the more the water crushes in. At some depth, the pressure becomes so great that her equipment fails and her light goes dark. She can never see the bottom because the very act of going deep enough guarantees the darkness. The Planck length is like that bottom. The tools you would need to reach it are the same tools that snuff out the view. This is why the Planck length may be a true limit, not a limit of our cleverness, but a limit of reality. Below it, the ordinary idea of distance stops making sense. You cannot measure a length smaller than the Planck length, because any attempt collapses into a black hole and erases the measurement. Location itself becomes fuzzy in a way no better machine can fix. Some physicists take this even further. If you truly cannot measure or even define a distance smaller than the Planck length, then maybe distances smaller than the Planck length simply do not exist. Maybe the Planck length really is the pixel of the universe, the smallest tile of space, and the smooth, endless staircase of ever finer distances was an illusion all along. Nobody has proven this yet, but the hint is impossible to ignore. Reality guards its smallest scale with the fiercest objects it has, sealing every attempt to peek behind the curtain. And that raises a haunting question about the space down there that we can never directly see. If we cannot look, what is actually happening in that hidden basement of reality? Our best theories offer an answer, and it is nothing like the calm, silent emptiness you would expect. If nature seals the smallest scale behind black holes, then those black holes are worth understanding on their own. Because the object standing guard over the basement of reality is the strangest thing Einstein's equations ever coughed up. A black hole forms when gravity utterly overwhelms everything else. Take a giant star, far heavier than the sun. For most of its life, it fights gravity by burning fuel in its core, pushing outward against the crushing weight of all its own mass. But the fuel runs out. When it does, nothing holds the star up. Gravity slams the whole thing inward, crushing an object wider than 1,000,000 Earths down toward a single point. What remains is a region where gravity is so ferocious that the dip in space-time becomes a bottomless pit. Roll back to Einstein's trampoline, the sheet that sags under heavy things. A black hole is a place where the sheet does not just dip, it plunges straight down into a hole with no floor, a funnel so steep that anything rolling near it slides in and never climbs back out. Around every black hole sits an invisible boundary called the event horizon. Cross it and you are gone. Not gone as in far away, gone as in cut off from the rest of the universe forever. To escape a black hole, you would have to travel faster than light, and nothing in the universe can do that. So light itself, the fastest thing there is, cannot climb out. That is why a black hole is black. It swallows every ray that wanders too close and gives nothing back. This is the guardian of the small scale. When you try to probe the Planck length and your energy collapses into a tiny black hole, that black hole throws up its event horizon and seals the region away. Whatever secrets lived at that scale are now behind the horizon, hidden from every eye in the cosmos. Here is a comparison to hold the horror of it. Imagine a whirlpool in a river, but a whirlpool with a special rule. Once a leaf drifts past the outer ring, no force on earth can pull it back upstream, because the water beyond that ring flows inward faster than anything can swim. The event horizon is that ring, except the thing flowing inward is space itself, pouring toward the center faster than light can run the other way. So the universe uses its most extreme object to guard its smallest scale. Every attempt to look too close builds a tiny sensor that clamps the view shut. Physicists sometimes call this cosmic censorship, the strange way nature seems to hide its most broken places behind horizons, keeping the madness inside out of sight. But a black hole is more than a guardian. It is a laboratory, because a black hole is the one place in the universe where gravity is unimaginably strong and the scale is unimaginably small at the very same time. It is exactly the collision zone we have been chasing, the place where Einstein's smooth fabric and the quantum storm are forced together with nowhere to hide. That makes black holes the greatest clue we have to the deepest secret in physics. Later, one of them will hand us a paradox so sharp it nearly broke the career of the most famous physicist of the modern age. But first, we have to ask what the fabric of space is actually doing down at the bottom, in the hidden realm the horizons protect. And the answer, first dreamed up by a bold physicist decades ago, sounds like the surface of a boiling sea. Down at the smallest scale, the calm, still emptiness you imagine does not exist. According to our best theory, space at the Planck length is a churning, violent, roiling mess. One physicist gave it a name that stuck. He called it space-time foam. That physicist was John Wheeler, a man famous for turning wild ideas into vivid pictures. He looked at what quantum mechanics demands and what gravity demands, put them together, and realized something shocking about empty space itself. On a large scale, space looks smooth and flat, like the surface of a calm lake seen from an airplane. Fly high enough, and the lake is a sheet of glass, perfectly still. But descend, drop from the airplane toward the water. As you get closer, the smooth glass reveals gentle waves. Closer still, and the waves break into churning whitecaps. Press your face right down to the surface, and you find a chaos of froth and spray and bursting bubbles, water leaping and crashing in every direction. The calm lake was an illusion of distance. Up close, it seethes. Wheeler said space-time is exactly like that. Seen from the scale of atoms or planets, space is smooth and gentle, the silky fabric Einstein described. But zoom down toward the Planck length, and the smoothness dissolves into a raging quantum foam. The fabric of space bubbles and tears and knits itself back together, over and over, faster than thought. Tiny bumps of curvature erupt and vanish. Little wormholes may briefly open and slam shut. The geometry of space itself flickers, refusing to hold a single steady shape for even an instant. Why does the foam appear? Because of the two rules we have already met. The quantum world says nothing at the smallest scale can hold still, and even empty space fizzes with borrowed energy. Gravity says energy bends space-time. Put those together at the Planck length, and you get space-time bending itself in random, violent bursts. Everywhere, all the time. The energy of the quantum jitters warps the very space they happen in, and the warping feeds back into more jitter. The result is a storm with no calm center. Here is the part that should stop you cold. In this foam, the everyday idea of distance falls apart. When space is boiling, the shortest path between two nearby points is no longer a clean straight line. It wanders through a landscape that keeps rearranging itself. Even the difference between here and there, between one direction and another, gets scrambled in the froth. Up, down, near, far. These words lose their sharp meaning inside the boil. Not everyone agrees the foam is real. It is a prediction, not a photograph, because no one can ever see it directly. Some physicists suspect the foam is milder than Wheeler imagined, or shaped differently, or perhaps not there at all. It sits below the Planck length, sealed behind the black hole sensors, forever out of direct reach. We can only reason our way toward it with math, but the core idea has haunted physics for decades and refuses to go away. If Wheeler is right, then the smooth stage on which everything happens, the quiet backdrop of space and time you take for granted, is a lie told by distance. Underneath, at the root of reality, everything is thrashing. And if space itself cannot hold a steady shape at the smallest scale, then a deeper worry follows. When physicists try to calculate anything at all in that foam, using the two theories together, the math does something worse than give a wrong answer. It gives no answer that any sane universe could allow. Sit with the foam a little longer, because its strangeness runs deeper than a boiling surface. In Wheeler's picture, it is not water that boils. It is geometry. The shape of space itself becomes a thing that cannot make up its mind. In the everyday world, geometry is the most solid thing there is. A triangle has three sides. Parallel lines never cross. The shortest way between 2 points is a straight line. These truths feel eternal, carved into the bones of reality. You build houses on them. You navigate ships with them. Geometry is the one thing you can always trust to stay put. At the Planck scale, that trust shatters. When space is foaming, the rules of geometry flicker from one instant to the next. In one tiny patch, for one tiny sliver of a moment, the space might curve one way. A blink later, it curves the other. Distances stretch and shrink at random. A path that was short becomes long. Directions twist. The whole notion of a fixed shape dissolves into a probability, a smear of maybes, just like the position of the electron we met earlier. Think of it this way. Picture a map of a city, printed on paper. Normally the map holds still. The streets stay where they are printed. Now imagine a map where the streets crawl and wriggle while you watch. Roads that were parallel suddenly cross. A shortcut becomes a detour. Two places that were neighbors drift apart, then snap back together. Trying to navigate that map would be a nightmare, because the ground beneath your route keeps rewriting itself. Space-time foam is a map like that, redrawing its own geometry billions upon billions of times faster than any clock can tick. There is an even stranger consequence hiding here. In the quantum world, things do not just jitter, they also tunnel. A particle can pass through a barrier it should not have enough energy to cross, appearing on the far side as if by magic. simply because quantum rules give it a small chance to be there. Now apply that to space itself. In the foam, the geometry of space can tunnel too, jumping from one shape to a completely different shape without passing through the shapes in between. Tiny bridges and holes might open between distant points and vanish before anything can use them. This means that at the root of reality, the very stage on which physics plays out has no fixed form. Einstein's theory treated space-time as a smooth, dependable arena, a fabric that bends but always stays whole and continuous. The quantum rules take that fabric and shred it into a flickering storm of shapes, each one existing only as a chance among countless others. And this is the exact heart of the war between the two theories. Einstein needs a smooth, definite space-time to write his equations on. Quantum mechanics says no such smooth, definite thing can exist at the smallest scale, because everything there must jitter, blur, and tunnel. One theory demands solid ground. The other insists the ground is made of quicksand. They cannot both be building on the same floor. So when physicists finally sat down and tried to do the honest thing, to write one set of equations for gravity that obeyed the quantum rules, they were trying to do physics on ground that would not stay still. They expected it to be hard. They did not expect the math to erupt into pure, screaming infinity every single time. And the reason it does exposes the deepest wound in the whole theory. When physicists finally tried to build a full quantum theory of gravity, the equations did not merely resist them. The equations detonated. Every calculation raced off toward infinity, and no trick could rein it back. To feel why this is so devastating, you have to understand what infinity means when it shows up in a physics equation. A good theory takes a question and gives a number. How strongly do these two things pull? How likely is this to happen? The answer should be a sensible amount, something you could in principle measure. When a calculation instead spits out infinity, it is not describing a very large effect. It is confessing that the theory has broken. Infinity is the sound a theory makes when it dies. Here is where the infinities come from. Remember that, at the smallest scales, the quantum world fizzes with restless activity, particles flickering in and out of empty space. To calculate anything precisely, physicists have to add up the contribution from all of these flickers, including the ones happening at smaller and smaller distances. For most forces, this sum stays under control. The tiny scale contributions get weaker and weaker, and the total settles onto a sensible number. For gravity, the opposite happens. As you add up the contributions from smaller and smaller distances, they grow instead of shrinking. Down at the Planck scale, the quantum jitters in gravity become monstrous, and the sum runs away to infinity. Every quantity you try to calculate inherits this disease. Ask a simple question about how two particles interact through quantum gravity, and the honest answer the math gives is a meaningless infinity. Picture trying to measure the total rainfall of a storm, but your rain gauge counts every drop twice as heavily as it should, then 4 times, then 8 times, growing without limit for every finer drop it detects. Your final total would climb to infinity, telling you nothing about the real storm. Something in the counting is fundamentally broken. Quantum gravity has exactly this sickness, and it is baked into the structure of the theory, not the arithmetic. Physicists have a word for a theory that behaves this way. They call it non-renormalizable, which is a grand name for a simple and brutal fact. The infinities cannot be tamed. There is no clever bookkeeping that sweeps them away and leaves a clean answer behind. When you try to combine Einstein's gravity with the quantum world using the ordinary tools, you get a theory that produces gibberish at the smallest scale, and no amount of skill can fix it. This is not a small technical snag that a sharper mathematician will clear up next year. It is a signpost. The infinities are the theory screaming that it has been pushed past the edge of where it works. They mark the exact place where our understanding runs out. Gravity, joined to the quantum world in the naive way, is telling us in the loudest possible voice that it is incomplete. For the other 3 forces of nature, Physicists eventually found ways to defeat the infinities and build theories that work with breathtaking accuracy. Those victories are among the greatest triumphs in the history of science. Gravity alone has refused every one of these methods. It stands apart, the one force that will not be tamed, the lone holdout against unification. Which raises the obvious question: if physicists manage to conquer the infinities for the other forces, why does that same magic fail so completely for gravity? What makes gravity so uniquely stubborn? The answer reveals something deep about what gravity truly is. To see why gravity is such a stubborn holdout, look at how physicists tamed the other three forces. Their victory was total, their method was brilliant, and it shatters against gravity for a reason built into gravity's very nature. Nature has four fundamental forces. Gravity is one. The other three are the electromagnetic force, which lights your screen and holds atoms together, and two nuclear forces that rule inside the atom's core, the strong force and the weak force. For decades, all three of these smaller forces suffered from the same infinity disease that plagues gravity. Try to calculate with them at the smallest scales, and the answers blew up. Then physicists discovered a rescue trick, an idea so powerful it earned several people the highest prizes in science. The trick is called renormalization. The idea is subtle, but the spirit of it can be caught. When the infinities appeared, physicists found they could gather all of them up and hide them inside a few basic quantities, like the mass and charge of a particle. Quantities they had to measure by experiment anyway. Once the infinities were tucked into those measured numbers, every other prediction of the theory came out clean, finite, and stunningly accurate. It sounds like cheating, and for a while even the physicists who invented it were uneasy, but it works with almost unbelievable precision. One of these renormalized theories predicts a certain property of the electron so accurately that it matches experiment to more than 10 decimal places, one of the finest agreements between theory and reality humans have ever achieved. The trick was no accident. It revealed something real about how those three forces are built. Now bring the trick to gravity. It fails, and it fails for a reason that goes to the heart of what gravity is. The renormalization trick only works when a theory has a limited number of infinities to hide. You gather them up, tuck them into a handful of measured quantities, and you are done. But gravity produces infinities of endlessly many different kinds. Every time you look at a smaller scale, a fresh type of infinity appears, one that needs its own hiding place. To sweep them all away, you would need not a handful of measured numbers, but an endless list of them, infinitely many. A theory that needs infinitely many measured inputs predicts nothing at all, because you can never finish measuring them. Why does gravity misbehave this way when the others do not? Because gravity is different in a way no other force is. The other three forces act on things sitting inside space-time, like players moving on a fixed field. Gravity is the field. Gravity is the shape of space-time itself. When gravity gets quantum jittery, it is space-time that jitters, the very stage everything else stands on. The other forces jiggle the actors. Gravity jiggles the theater. Here is a comparison. Imagine trying to film a movie where the actors move around normally. Hard, but doable. Now imagine the camera, the set, the floor, and the walls are all shaking and reshaping themselves at random too. There is no steady ground to film against, because the ground is part of the chaos. That is gravity. It cannot be tamed the way the others were, because it is woven into the fabric that every taming trick assumed would stay still. So gravity stands alone, the one force that refuses to join the others in a single clean theory. And its stubbornness points at something even deeper. If gravity is quantum, then like every other force, it should have a messenger, a particle that carries it. That particle has a name, and catching even a single one of them may be impossible. Every force in nature works by passing a messenger, and if gravity is truly a quantum force, it must have a messenger too, a particle so faint that catching one may lie beyond anything humans can ever build. Think about how the other forces operate. When two magnets push apart, they are not connected by an invisible rope. They are trading messenger particles back and forth, tiny packets of light called photons flying between them, carrying the electromagnetic force. The strong force inside atoms has its own messengers. The weak force has its own. Each force is a game of catch, with particles thrown between the players to push and pull them around. So if gravity plays by quantum rules, it should work the same way. Two objects pulling on each other through gravity should be tossing a gravity messenger back and forth. Physicists gave this particle a name before anyone had ever seen a hint of it. They call it the graviton. It would be the smallest possible piece of gravity, a single quantum grain of the pull that shapes the cosmos. The theory even tells us what the graviton should be like. It must have no mass, so that gravity can reach across infinite distance from here to the farthest galaxy. It must travel at the speed of light, which fits perfectly because we have already caught ripples in space-time, gravitational waves, arriving at exactly light speed. A gravitational wave in the quantum picture would be a vast swarm of gravitons moving together, the same way a beam of light is a swarm of photons. Now for the crushing problem. Gravity is so unspeakably weak that a single graviton would be almost impossible to detect. Remember, a small magnet beats the entire pull of planet Earth on a paperclip. Gravity only feels strong to us because the Earth is enormous, and every scrap of its mass adds up. The pull from any single particle is beyond feeble, and the messenger that carries such a feeble force is the faintest whisper in all of physics. Here is how faint. Physicists have estimated that to build a machine capable of catching one lone graviton using anything like current methods, you might need a detector so massive and so sensitive that constructing it could be flatly impossible, requiring resources beyond a whole civilization. Some have calculated that a graviton detector working on ordinary principles might have to be as heavy as a planet parked beside a neutron star, and even then it would catch almost nothing. The single graviton may be the one particle we can predict exists yet never hold in our hands. Picture standing on a beach during a roaring storm. Giant waves crash in, easy to see, the way we can detect gravitational waves rolling in from colliding black holes. But those waves are made of countless individual water molecules. Now try to catch one single molecule out of the crashing surf and prove it exists on its own. The wave is obvious. The single grain is hopeless. That is the gulf between detecting gravitational waves, which we have done, and detecting one graviton, which may forever escape us. So gravity may have a messenger we can never meet, a ghost particle, demanded by the theory, hiding below the threshold of everything we can measure. Its faintness is a symptom of the same weakness that lets gravity and the quantum world avoid each other almost everywhere. Because there remains one place where gravity is not weak at all, one place where it grows so violent that it crushes matter out of existence and drives our equations straight off a cliff into the infinite. We are about to fall into it, fall into a black hole, and at the very center waits the most broken place in the universe, a point where our finest theory does not bend or strain, it simply dies. Physicists call it a singularity, and it is where gravity finally stops being weak and becomes a monster. We met the black hole as a guardian, sealing off the small scale behind its event horizon. But cross that horizon and keep falling, and something far stranger lies ahead. All the mass of the collapsed star keeps rushing inward. Nothing stops it. There is no known force strong enough to halt the collapse. The matter crushes down and down toward the center, packing tighter and tighter with no floor to catch it. According to Einstein's equations, that matter is crushed into a single point of zero size, a speck with no width, no volume, nothing. And into that speck of no size, the entire mass of a giant star is squeezed. When you divide a huge amount of mass by a volume of zero, the math gives an answer that means the theory has failed. The density becomes infinite. The curve in space-time becomes infinite. The dip in Einstein's trampoline plunges down forever with no bottom at all. This is the singularity, and it is the ultimate collision of everything we have been chasing. Here, gravity is not the feeble force that a magnet beats. Here it is absolute, overwhelming, infinite. And here the scale is not large but smaller than any particle crushed toward a point. Enormous gravity and tiny scale, together, in the same place, at full strength. This is the exact war zone, where Einstein's theory and the quantum world are forced into the same room with nowhere to run. And Einstein's theory, standing alone in that room, breaks. It hands back infinities, the same scream of failure we saw before. The equations that describe everything so beautifully everywhere else give nonsense at the singularity. They divide by zero. They point to a place of infinite density that no sane universe should contain. Here is a comparison to feel the wrongness of it. Imagine a road on a map, and you follow it toward a certain point. As you get closer, the road narrows, and the map tells you the road slope is getting steeper. Closer still, steeper still. Right at the point, the map says the slope is infinite, straight up, a cliff of impossible height with no top. You know instantly the map is broken there. No real road does that. The infinity is the map, confessing it cannot describe that spot. The singularity is that broken point on the map of reality. Most physicists are certain the singularity is not truly real. A point of genuinely infinite density almost surely does not exist. Instead, the infinity is a giant warning sign, flashing at the exact place where Einstein's gravity must give way to a deeper theory we do not yet have. Something happens at the center of a black hole, something governed by quantum gravity, the missing theory. But what that something is, nobody knows, because we have no working theory to describe it. The singularity is hidden from us, sealed behind the event horizon, forever out of sight. We can never send a probe to report back. Whatever truth lives at the heart of a black hole stays locked away. But there is one singularity we cannot look away from, one that is not hidden behind any horizon, one that every particle in your body came out of at the beginning of time. There is one singularity that no horizon hides, one place where our physics divides by zero in full view, and you came out of it. Every atom in your body traces back to that instant, the first moment of the universe, the Big Bang. Rewind the cosmos. Right now, the universe is expanding. Every galaxy rushing away from every other, the whole thing swelling like a balloon being blown up. Run the film backward, and everything rushes together instead. Galaxies pile in. Space shrinks. The universe grows hotter and denser as you press further into the past. Keep rewinding, past the first stars, past the first atoms, into a fireball of unimaginable heat, all of reality squeezed into a smaller and smaller space. Keep going, and the equations lead to a terrifying conclusion. At the very beginning, the entire universe, all the matter and energy that would ever become every star and galaxy in person, was crushed into a single point of zero size. Infinite density, infinite temperature, infinite curvature of space-time. The same broken infinities we found inside the black hole, except this time the singularity is not off in some distant collapsed star. It is the birthplace of everything. This is the Big Bang singularity, and it is the deepest embarrassment in all of cosmology. Our best theory of the universe, Einstein's gravity, describes the expansion of the cosmos across billions of years with stunning success. It predicts the leftover glow of the early fireball, still faintly humming across the sky today, and telescopes find it exactly where the theory says. But run the same theory back to the very first instant, and it collapses into a singularity, a moment where the math means nothing. So the honest truth is startling. We do not know what happened at the birth of the universe. Our finest theory breaks at the one moment we most want to understand. The equations say the universe began at a point of infinite density. And infinite density is the theory admitting defeat. The origin of everything sits behind a wall of shattered math. Here is the strange comfort in it. The Big Bang singularity is a promise that a deeper theory must exist. Just as the infinity inside a black hole flags the place where quantum gravity must take over, the infinity at the birth of the cosmos flags the same missing theory, screaming that Einstein's gravity was only ever part of the story. Whatever really happened in that first instant was ruled by quantum gravity, the theory we do not yet have. And the stakes here are enormous. Solve quantum gravity, and you might finally learn what came before the Big Bang, or whether that question even has meaning. You might discover that the universe did not begin at a point at all, but bounced out of an earlier cosmos, or budded off from something larger, or emerged in some way no human has yet imagined. The answer to where everything came from is locked inside the theory we are chasing. Picture a clock running backward toward a moment marked 0. As the hands sweep toward that mark, they spin faster and faster, until right at 0, they would have to spin infinitely fast, which no clock can do. The infinity tells you the clock cannot reach that mark. Something else must take over before it gets there. The Big Bang is that unreachable mark on the clock of time. By now, a question may be gnawing at you. When we say gravity breaks down, what does breaking down actually mean? Gravity clearly still works. So what exactly is falling apart? The answer is subtle, and it changes everything about how to think of this whole mystery. By now, the phrase has come up again and again. Gravity breaks down. The theory dies. The math shatters. But gravity plainly keeps working. Planets keep orbiting. Things keep falling. So it is worth being precise about what actually breaks, because the truth is subtle and it reshapes the whole mystery. When physicists say gravity breaks down at the smallest scale, they are making a careful claim. Gravity itself, the real thing out there in the universe, keeps doing whatever it does. Inside a black hole, at the birth of the cosmos, gravity is busy, ferocious, entirely real. What breaks is our description of it, our equations, our theory. The tools we use to predict and understand fail, even though the universe carries on untroubled. This distinction matters enormously. The infinities we keep meeting are not features of reality. A real black hole does not contain a genuine point of infinite density. The infinity lives in our math, not in the world. When the equations spit out infinity, they are confessing their own limits, waving a flag that says, our theory has been pushed past the region where it applies. The universe knows exactly what to do. We are the ones who run out of language to describe it. Here is a comparison that makes it clear. Imagine an old map of the world from centuries ago, drawn by sailors who had only explored part of the globe. Near the edges of the known world, where no one had sailed, the mapmakers wrote a warning, "Here be dragons," and left the rest blank or filled it with monsters. The dragons were not real. The ocean out there was ordinary water, with real coastlines and real islands. The dragons only marked the edge of the mapmaker's knowledge. The infinities in physics are the dragons on our map of reality. They mark where our understanding stops, not where the universe stops. So the smallest scale, the Planck length, the singularities, the boiling foam, all of these are regions where our current map runs out and the dragons appear. The territory is real. Something definite is happening in the heart of a black hole and in the first instant of the universe. We simply lack the map to chart it. Our two great theories, gravity and the quantum world, are each accurate maps of their own regions, and they fail only where their regions overlap, at the smallest and most extreme scale. This is actually a hopeful way to see the problem. The breakdown is a signpost, telling us precisely where a deeper, truer theory must be hiding. Every place our equations scream infinity is a place marked on the map with an arrow that says, dig here. The failures are not dead ends, they are directions. They point straight at the undiscovered theory of quantum gravity, the map that would finally chart the regions our current maps abandon, and there is real reason to believe such a map exists. The universe out there does not divide by 0. It does not actually produce infinities. It runs on smoothly through every black hole heart and cosmic beginning, following some set of rules that never breaks. Those rules are real. They are out there, waiting. Our job is to find them. So the search for quantum gravity is a search for the missing pages of the map, the pages that would replace every dragon with a real coastline. It is the greatest exploration in modern science, aimed not at a distant land, but at the smallest scale of reality itself. And the first genuine clue to those missing pages came from the last place anyone expected. It came from a black hole that seemed to be committing a crime against the deepest law of the quantum world. The first real crack of light in this darkness came from a puzzle so sharp it nearly broke the most famous physicist of the modern age. A black hole, it turned out, appears to commit a crime against one of the deepest laws in all of physics. The law it seems to break is about information. In the quantum world, information is sacred. It can never be truly destroyed. Burn a book, and it looks like the information in it is gone forever. But in principle, if you could track every particle of smoke and ash and every ray of light from the flames, you could reconstruct every word. The information is scrambled beyond any hope of practical recovery, yet it still exists, scattered in the details. This is a bedrock rule. The universe keeps a perfect record. Nothing is ever fully erased. Now throw that book into a black hole. It crosses the event horizon and vanishes, pulled down toward the singularity. The information seems gone, but a physicist could shrug and say it is merely hidden inside, sealed behind the horizon but still there in some form. Troubling, but survivable. Then came Stephen Hawking, and he found something that turned the trouble into a crisis. Hawking proved that black holes are not truly black. They slowly leak. They give off a faint trickle of particles and shrink over unimaginably long stretches of time. Wait long enough, and a black hole evaporates completely, fading away into nothing but a bath of featureless radiation. Follow the horror of it. You threw a book into the black hole, carrying all its information. The black hole slowly evaporates, giving off radiation that Hawking showed carries no memory of what fell in. Eventually, the black hole is gone, the book is gone, and the radiation left behind holds no trace of the words. The information has not been hidden, it has been destroyed, erased from the universe. The sacred law is broken. This is the black hole information paradox, and it set off one of the fiercest battles in the history of physics. On one side stood Einstein's gravity, which said the information falls in and is lost when the black hole evaporates. On the other side stood quantum mechanics, which insisted, with all its towering precision, that information can never be destroyed. Two flawless theories, giving opposite answers about the fate of a single book. The war between them made concrete. Hawking himself argued for years that the information really was lost, that black holes could erase reality's records. Other physicists were horrified, because if information can vanish, then the entire framework of quantum mechanics, the most successful theory ever built, would come crashing down. The stakes could not be higher. One of the two pillars of physics had to be wrong. Here is a way to feel the paradox. Imagine a shredder that does not just cut paper into strips, but makes the words themselves cease to have ever existed, so that no power in the universe, not even a perfect all-seeing recorder, could ever say what the paper had said. Ordinary shredders scramble. This one annihilates. Quantum mechanics swears no such shredder can exist. A black hole seems to be exactly that shredder. The paradox burned for decades, and slowly, most physicists came to believe that Hawking was wrong, that the information must escape somehow, that quantum mechanics holds and gravity's simple picture is the part that fails. But saving the information demanded a price. It forced physicists toward ideas about reality so strange that they redraw the map of what space itself is. And it all begins with that faint trickle of radiation, the glow Hawking discovered, which was the very first place gravity and the quantum world ever shook hands without screaming. That faint trickle Hawking discovered deserves a closer look, because it is a small miracle. For one brief calculation, gravity and the quantum world stopped fighting and worked together. The glow of a black hole is the first genuine bridge ever built across the deepest divide in physics. Recall the setup. A black hole was supposed to be perfectly black, a one-way door that swallows everything and gives back nothing. That is the pure gravity picture, straight from Einstein. But Hawking asked what happens when you take the quantum world seriously right at the edge of the event horizon, in the fizzing vacuum where particles constantly flicker in and out of empty space. Here is the beautiful mechanism he found. Remember that empty space is never truly empty. All across the vacuum, pairs of particles pop into existence for a fleeting instant and then find each other and vanish again, borrowing energy and paying it back so fast that the universe barely notices. This happens everywhere, all the time, including right at the edge of a black hole. Now watch what happens at the horizon. A pair of particles flickers into being right at the edge. Normally, they would rejoin and disappear, but at the horizon, one of the pair falls inward across the point of no return, while the other escapes outward into space. They can never reunite, because one is trapped forever inside and one is free. The escaping particle flies away from the black hole as real radiation. The black hole has glowed. To pay for that escaped particle, the black hole loses a tiny sliver of its mass. Do this countless times, over spans of time so vast they dwarf the current age of the universe, and the black hole slowly shrinks, evaporating particle by particle until nothing remains. That is Hawking radiation, and its discovery was a thunderclap because it was the first time anyone had ever combined gravity and quantum mechanics into a single calculation and gotten a sensible, finite, believable answer. For that one result, the two warring theories cooperated. Hawking used Einstein's curved spacetime to describe the black hole and the quantum rules to describe the flickering vacuum at its edge, and the two fit together to predict something concrete. The glow even has a temperature, a precise number set by the black hole's size. Smaller black holes glow hotter and evaporate faster. Giant ones glow so faintly and fade so slowly that they will outlast almost everything else in the cosmos. Here is a comparison to hold it. Picture a still pond at night, its surface perfectly dark and calm. Now imagine that right at the edge of a hidden whirlpool, the water constantly throws up tiny sprays of droplets. Most fall back in, but some, thrown from just the right spot, land outside the pool and trickle away down the bank. Drop by drop, the whirlpool bleeds itself dry, all because of the sprays dancing at its lip. The dark pond was leaking all along, in a way you could only see by looking at its very edge. This glow is treasured by physicists because it is a rare true clue, a place where the missing theory of quantum gravity peeks through into something we can calculate. And it deepened the information paradox at the same time, because the escaping glow seemed to carry no memory of what fell in. That tension forced physicists to look harder at black holes, and what they found in the numbers pointed at a secret about reality so profound it suggests the world may be nothing like it appears. It began with a simple question. Exactly how much information can a black hole hold? Chasing the information paradox led physicists to a simple question with a shocking answer. How much information can a black hole hold? The answer broke a rule so basic that no one had ever thought to question it, and it hinted that reality is built in a way nobody expected. Ask how much information you can stuff into any ordinary region of space, and common sense gives a clear reply. Information takes up room in 3 dimensions, so a bigger volume should hold more. A large warehouse stores more boxes than a small closet, and if you double every dimension of the warehouse, its volume grows 8-fold, and it holds roughly 8 times as much. Capacity should scale with volume. That feels obvious. Unbreakable. Written into the geometry of space. Black holes shattered that expectation. When physicists worked out how much information a black hole can contain, the answer did not scale with its volume, with the space inside it. It scaled with its surface area, with the size of the event horizon wrapping around it. The amount of information a black hole holds is set by the area of its boundary, the 2-dimensional surface, not the 3-dimensional space within. Sit with how bizarre that is. It is as if you had a warehouse, and no matter how you tried, the total number of boxes it could ever hold depended only on the area of its outer walls, never on the vast space inside. Double the walls, and you could store 4 times as much, following the area, not the 8-fold you would expect from the volume. The interior seems almost not to count. Everything the black hole can know is written on its skin. And a black hole is special here, because it holds the maximum possible information for its size. You cannot cram more into any region than you could fit into a black hole of the same size, because trying to add more would make the region collapse into a black hole itself. So the black hole sets the ultimate limit for all of space. And that limit is always an area, a surface, a 2-dimensional boundary. This discovery sent a jolt through physics. It suggested that the true capacity of any chunk of the universe, the real count of everything that can happen inside it, is fixed by the area of its border rather than the volume it encloses. The 3-dimensional inside, the part that feels so real and solid to us, might carry less fundamental reality than the flat surface around it. Here is why that is a clue, and not just a curiosity. Information is not some side detail in modern physics. Information is the deepest currency there is, the true count of all the different ways a system can be arranged. If the information capacity of space lives on surfaces rather than in volumes, then something is profoundly strange about how space itself is put together. The dimension of depth, of interior, of volume may not be as fundamental as it looks. Physicists stared at this surface rule and asked a daring question. What if the reason all the information lives on the boundary is that the boundary is where the real action is? What if the 3-dimensional world inside, the space you move through, is somehow a projection, a picture generated by information stored on a distant 2-dimensional surface? That question sounds like madness. It is also one of the most serious ideas in theoretical physics, and it may hold the key to quantum gravity. It has a name that captures its strangeness perfectly. They call it the holographic principle. The surface rule led physicists to an idea so radical it sounds like a fever dream. The 3-dimensional world you live in, with all its depth and space and distance, might be a kind of projection generated by information stored on a distant, flat, 2-dimensional surface. They call it the holographic principle, and it may be the deepest clue we have. Start with an everyday hologram, the shimmering image on a credit card or a fancy sticker. That image looks 3-dimensional. Tilt it and you seem to see around the object, as if it had real depth. But the actual hologram is flat, a thin 2-dimensional sheet. All the information needed to build the full 3-dimensional image is encoded in patterns on that flat surface. The depth is an illusion conjured from a flat code. The holographic principle makes the staggering suggestion that the entire universe might work the same way. Everything happening inside a region of space, every particle, every force, every event with its full 3-dimensional richness, could be completely described by information living on the 2-dimensional boundary around that region. The inside would be the hologram. The boundary would be the flat sheet holding the real code. Depth itself, the 3rd dimension, would be a projection. This idea did not come from wild speculation. It came straight from the black hole surface rule, from the hard fact that information scales with area rather than volume. Physicists reasoned that if all the information about a region can be stored on its boundary, then perhaps the boundary is the true description, and the 3-dimensional interior is a rich, convincing illusion built from that boundary information. For years, this was a beautiful guess, with no solid math behind it. Then, a physicist found a specific, precise example where it provably works. He described a particular kind of universe and showed, with rigorous mathematics, that everything happening in its 3-dimensional interior, including gravity itself, is perfectly mirrored by a theory living on its 2-dimensional boundary, a theory with no gravity at all. 2 descriptions, one with gravity in 3 dimensions and one without gravity in 2, turned out to be the exact same physics wearing different clothes. This was a bombshell. And here is why it matters so much for our search. In that example, gravity in the interior emerges out of a flat boundary theory that has no gravity in it. Gravity is not fundamental there. It is a consequence, a projection, something that arises from the deeper flat description. If that is how our universe works too, then the reason gravity has resisted every attempt to quantize it might be that we have been treating it as fundamental when it is really emergent, a shadow cast by something simpler underneath. Picture a movie projected onto a screen. The film feels vast, full of space and motion and depth, but all of it is encoded on a flat strip of film, a two-dimensional surface running through the projector. The three-dimensional world on the screen is real to the story, yet it is generated entirely by the flat code. The holographic principle whispers that our universe might be a projection like that, with the true information living on a boundary we cannot easily see, and the space we move through spun out of it. Nobody knows for certain that our universe is holographic. The rigorous example works for a universe shaped differently from ours, and extending it to our own cosmos remains unfinished. But the principle has become one of the guiding lights of the search for quantum gravity, a signpost pointing toward a reality far stranger than solid space. Holography grew out of one bold attempt to fix the infinities of gravity, a theory that reimagined the smallest building blocks of everything. In it, particles are not points at all, but tiny strings, endlessly vibrating. The holographic idea grew out of the boldest attempt ever made to unite gravity with the quantum world. This attempt begins by throwing away one of the oldest assumptions in physics. The smallest building blocks of everything, it says, are not tiny points at all. They are tiny strings, and they never stop vibrating. To feel why this helps, go back to the root of the infinity problem. When physicists calculate quantum gravity, the answers blow up because they add contributions from smaller and smaller distances, all the way down to zero. Particles were always pictured as points, dots of zero size, and a point of zero size lets you keep zooming in forever, down to distances where the math explodes. The zero size point is a doorway that leads straight to the infinities. String theory slams that doorway shut. Instead of points, it says the fundamental objects are tiny loops and threads of vibrating energy, each about the size of the Planck length, the smallest meaningful distance we met earlier. Because a string has an actual size, you cannot zoom in below it. There is no point of zero size to blow up the math. The string smears out the interactions over a tiny but real length, and the infinities that plagued gravity soften and melt away. That alone would be interesting. But string theory does something far more dramatic, and it is the reason so many physicists have devoted their lives to it. When you work out the different ways a string can vibrate, like the different notes a guitar string can play, each vibration pattern behaves like a different particle. One pattern of vibration looks like an electron, another looks like a quark, another looks like a photon of light, and buried in the list of vibrations, appearing automatically without anyone forcing it, is a pattern with exactly the properties of the graviton, the messenger of gravity we searched for earlier. String theory does not have to assume gravity. Gravity falls out of it, unavoidably, as one of the notes the string can play. A theory built to describe tiny vibrating threads coughs up gravity for free. For many physicists, that was the most thrilling moment in the whole enterprise. Here is the comparison that captures it. Think of a single guitar string. Pluck it one way, and it sounds one note. Pluck it another way, and it sounds a different note. The string is one simple thing, yet it can produce an entire range of tones depending on how it vibrates. String theory imagines the whole universe as music played on countless tiny strings, and every particle you have ever heard of, every speck of matter, and every ray of force is just a different note in that cosmic song. Even gravity is one of the tones. So, string theory offers a breathtaking promise. One kind of object, the vibrating string, giving rise to every particle and every force, gravity included, all in a single framework, with the deadly infinities tamed. It would be the theory of everything, the map that charts all the regions where our current maps fail. It is one of the leading candidates for quantum gravity, and thousands of the sharpest minds in physics have poured decades into it. But the strings demand a steep and shocking price. For the math to work, for the vibrations to come out right and the infinities to truly vanish, the universe cannot have only the 3 dimensions of space we see. It must have more, hidden dimensions, curled up so small that no eye and no machine has ever found them. String theory hands us gravity for free, but it demands a price so strange it sounds like fantasy. For the theory to work, the universe cannot have only the 3 directions of space we know. It must have extra dimensions, hidden ones, folded up so small that we have never noticed them. You live in 3 dimensions of space. You can move left and right, forward and back, up and down, 3 directions, and every place you have ever been is some combination of them. This feels complete. It feels like all the room there could possibly be. String theory says otherwise. When physicists work through the math of vibrating strings, the equations only come out consistent if space has more than 3 dimensions. Several more, curled up and hidden. How can extra dimensions exist without us seeing them? The answer is that a dimension can be rolled up so tightly that it becomes invisible at everyday scales. Here is the classic way to picture it. Imagine a long garden hose stretched across a field. From far away, the hose looks like a simple line, one-dimensional, with only length. You could mark any point on it with a single number, how far along it is, but walk right up to the hose, and you see it has another dimension you missed from a distance. You can move around its circumference, wrapping around the tube. That second dimension was there all along, curled into a tiny circle, invisible until you got close enough. String theory says the extra dimensions of space are like the wrapped around direction of that hose, curled into circles and more elaborate shapes, far smaller than an atom, smaller even than a proton, down near the Planck length. At every single point in the space you move through, these tiny extra dimensions are folded up, too small to see, too small to enter, yet shaping everything. We miss them for the same reason a distant hose looks like a line. We are simply too big and too far to notice the curl. And these hidden dimensions are not idle decoration. In string theory, their exact shape decides how the strings vibrate, and how the strings vibrate decides what particles exist and how the forces behave. Fold the extra dimensions one way, and you get one set of particles and forces. Fold them another way, and you get a completely different universe with different physics. The shape of the hidden dimensions writes the laws of nature we observe. This leads to a dizzying possibility. There may be an astronomical number of different ways to fold the extra dimensions, each producing a different set of physical laws. Some physicists estimate the number of possible foldings is so vast it dwarfs the number of atoms in the observable universe. Each folding would be a different possible universe, with different particles, different forces, different constants. Our universe would be just one folding among a near endless landscape of them. Here is the unsettling beauty of it. If that landscape is real, then the specific laws of our universe, the ones that let stars burn and atoms form and life arise, might be just one option among a mind-bending multitude, and we live in this one because it happens to allow beings like us to exist and wonder about it. String theory is elegant, powerful, and haunted by a hard problem. Those extra dimensions are so small, near the Planck length, that we may never be able to test whether they are truly there. A theory of everything that might sit forever beyond experiment. That difficulty pushed other physicists toward a completely different vision of quantum gravity, one that does not add hidden dimensions, but instead tears apart the oldest assumption of all, that space is smooth. While some physicists chased vibrating strings and hidden dimensions, others took a completely different road. They kept the 3 dimensions of space we know, but they attacked a far older assumption, the belief that space is smooth. In their theory, space is woven, stitched together from tiny threads, like a piece of chainmail seen from a distance. This approach is called loop quantum gravity, and it starts from Einstein's own insight. Einstein taught that gravity is the geometry of spacetime, the bending and shape of the fabric itself. Loop quantum gravity takes that seriously and asks the natural next question. If gravity is the shape of space, then to make gravity quantum, you must make space itself quantum. You must apply the jittery, chunky rules of the quantum world directly to the fabric of space. And when these physicists did that, they found something remarkable. Space stopped being smooth. In their equations, space is built from tiny, discrete pieces, indivisible chunks woven together into a network. The smooth, continuous fabric Einstein imagined turns out, in this theory, to be an illusion created by looking from too far away. Zoom down to the Planck length, and the fabric resolves into a fine weave of individual threads and nodes, a structure they describe using loops, which is where the theory gets its name. Here is the comparison that makes it click. Look at a photograph on a screen from across the room, and it appears perfectly smooth, colors blending seamlessly into one another. Walk up close, press your eye to the screen, and the smoothness dissolves into a grid of tiny separate pixels, each a single block of color, with nothing in between them. The smooth image was an illusion of distance. Up close, it is a mosaic of discrete tiles. Loop quantum gravity says space is exactly like that screen. From afar, it looks like a continuous fabric. Up close, at the Planck scale, it is a network of discrete grains. This idea directly heals the infinity problem that destroyed ordinary quantum gravity. Remember, the infinities came from adding up contributions at smaller and smaller distances, all the way down to zero. But if space itself has a smallest possible chunk, a shortest possible thread near the Planck length, then there is no down to zero. The weave of space stops at a smallest size. There is no infinitely small distance to fall into, so the sum never runs away to infinity. The chunkiness of space acts as a natural floor, a bottom that catches the falling math before it explodes. Loop quantum gravity paints a startling picture of the world. The space around you right now, which feels so smooth and continuous, would actually be a vast web of unimaginably tiny loops, each one about the size of the Planck length. Every cubic inch of the room you occupy would contain an incomprehensible number of these woven threads, so many that the fabric looks perfectly seamless to your enormous, clumsy senses. The smoothness of the world is a grand illusion, and the truth is a fine chainmail of geometry, stitched together loop by loop. This theory makes bold, specific claims. It says there is a smallest possible area and a smallest possible volume in the universe, sizes below which space cannot be divided any further. Just as you cannot have half a pixel on a screen, space comes in indivisible grains, and those grains are the true bottom of reality. If space itself is chopped into smallest possible chunks, then a strange and thrilling consequence follows. The whole idea of the smooth, endlessly divisible universe was wrong, and reality is granular at its root. That claim deserves a chapter of its own. Loop quantum gravity makes a claim so bold it changes how you picture the ground beneath your feet. Space is not smooth. It comes in smallest possible chunks, grains of area and volume that cannot be split any further. Reality, at its root, is built from pixels. Return to the screen for a moment. A digital image seems to show smooth curves and gentle gradients, but it is secretly made of pixels, tiny squares of single color. There is a smallest possible piece of that image, 1 pixel, and you cannot have anything finer. You cannot display half a pixel or a quarter of a pixel. The pixel is the atom of the picture, the indivisible unit below which the image simply does not exist. Loop quantum gravity says space works the same way. There is a smallest possible area, roughly the size of the Planck length squared, and you cannot have any patch of space smaller than that. There is a smallest possible volume, roughly the Planck length cubed, and you cannot have any region of space tinier than that single grain. Space is quantized, chopped into indivisible units, Exactly as light is chopped into individual photons and matter into individual particles, the fabric of reality has a smallest thread, and below it, the very idea of a smaller size loses all meaning. This resolves the ancient question we asked long ago: can you keep cutting space in half forever? In this theory, the answer is a firm no. Cut a region of space down, and eventually you reach a single grain of volume, the smallest chunk there is. Try to cut that grain, and you find there is nothing to cut. You have hit the pixel of the universe. The endless, bottomless staircase of ever finer distances was a fantasy. The staircase has a last step, and that step sits at the Planck scale. Feel how strange and beautiful this is. When you wave your hand through the air, it feels like you are sweeping through smooth, continuous, empty space. But if loop quantum gravity is right, your hand is actually moving through a fine mesh of discrete grains, hopping from one chunk of space to the next, far too quickly and smoothly for you to ever feel the graininess. The smoothness you experience is an average, the blur of countless tiny pixels seen by senses far too coarse to resolve them. Reality is pixelated, and we are simply too big to notice. This granular picture also reshapes how we think about the broken places we visited earlier. Remember the singularity, the point of supposed infinite density at the center of a black hole and at the birth of the universe, where Einstein's equations divided by zero. In a universe made of smallest possible chunks, a true point of zero size cannot exist. There is always a smallest grain in the way, so the infinite density may never actually form. The singularity might be replaced by something finite, a densest possible grain of space that gravity crushes matter into, but can crush no further. This hints at a stunning possibility for the Big Bang. If the crushing cannot continue to infinity, then rewinding the universe might not end in a singularity at all. It might end in a bounce. The universe could have collapsed from an earlier cosmos, squeezed down to the smallest possible size, and then rebounded outward into the expansion we call the Big Bang. The beginning of everything might be a rebound rather than a birth from nothing. And if space itself is granular, a question rises that is stranger still. What about time? Is the flow of moments also chopped into smallest possible ticks? Or is time something even more fragile? Something that might not be fundamental at all? If space is granular, the next question is unavoidable and deeply unsettling. What about time? We treat time as the steady river. Everything floats down, always flowing, always real. But at the smallest scale, some theories suggest that time itself might come in chunks, or worse, that time might not be fundamental at all. Start with the gentler idea. Just as space might be built from smallest possible grains, time might be built from smallest possible ticks. There could be a shortest possible duration called the Planck time, the amount of time it takes light to cross a single Planck length. It is unimaginably brief, so short that the number of Planck ticks in a single second is larger than the number of seconds that have passed since the Big Bang, many times over. If this is right, then time does not flow smoothly like a river. It advances in tiny, discrete jumps, like the frames of a film clicking forward one at a time, far too fast for anyone to sense the flicker. That alone is a strange thought. The smooth passage of time you feel would be an illusion, the blur of countless frames flashing by, each one a single, indivisible tick. Between one tick and the next, there would be no in-between, no fraction of a tick, nothing. Time would be a stack of frozen moments played in sequence. But some theories of quantum gravity go much further, into territory that unsettles even the physicists who work there. They suggest that time might not be a basic ingredient of reality at all. When physicists write down certain equations that try to describe the whole universe through quantum gravity, something eerie happens. The variable for time drops out. It vanishes from the equation entirely. The math describes a universe that simply is in all its configurations at once, with no ticking clock built into its foundations. This is one of the deepest puzzles in the whole search, and it is called the problem of time. If the fundamental equations of the universe contain no time, then where does the powerful, undeniable flow of time we all experience come from? Why do we remember the past and not the future? Why does time seem to march forward if the deepest laws do not mention it? Here is one way physicists try to picture the answer. Imagine a thick book sitting closed on a shelf. Every page of the story already exists, all at once, printed and complete. The book does not flow, it just is, all its pages present together. Yet, if you are a character living inside the story, reading through it, page by page, you experience a flow, a sequence, a before and after. The flow of time, in this picture, is what the universe feels like from the inside, even though the universe as a whole simply exists all at once, every moment printed and present. If this is true, then time as you know it, the relentless forward rush of your life, might be an emergent feature, something that arises for beings inside the universe, rather than a fundamental thread woven into reality's foundation. Time would be a story we experience, not a girder holding up the cosmos. Nobody has proven any of this. The problem of time remains wide open, one of the sharpest thorns in the search for quantum gravity. But it points toward a possibility more radical than anything we have met so far. If time might not be fundamental, and if space is looking more and more like an emergent illusion built from grains, then perhaps neither space nor time is the true bottom of reality. Perhaps both of them arise from something deeper, something with no space and no time in it at all. We have watched space turn granular and time threaten to dissolve. Now comes the most radical idea in the entire search, the one that turns everything upside down. Perhaps space and time are not the foundation of reality at all. Perhaps they emerge from something deeper, something with no space and no time in it, something woven from the quantum connections between things. This idea grew out of the holographic discoveries and the black hole information paradox, and it centers on one of the strangest features of the quantum world, called entanglement. When two particles become entangled, they form a single linked system, so that measuring one instantly tells you about the other, no matter how far apart they sit. Einstein hated this and called it spooky action at a distance, but it is real, tested countless times, one of the most solid facts in physics. Entangled particles share a connection that ignores the space between them entirely. Here is where it gets breathtaking. In recent years, physicists studying the holographic examples noticed something astonishing. When they looked at how the two-dimensional boundary theory built up the three-dimensional space inside, they found that the space was stitched together by entanglement. The more strongly two regions on the boundary were entangled, the closer together they appeared in the three-dimensional interior. Weaken the entanglement, and the two regions drifted apart in space. Cut the entanglement entirely, and the space between them tore in two. Sit with what that means. Distance itself, the space between things, seemed to be woven out of quantum entanglement. Two places are near each other because their quantum connections are strong. Two places are far apart because their connections are weak. Space is not the stage on which entanglement happens. Space is what entanglement builds. The fabric of space-time might be knitted, thread by thread, from the connections between quantum bits of information. Here is a comparison to hold this dizzying idea. Imagine a vast social network, a web of people connected by friendships. There is no physical space in that network to begin with, just people and the links between them. But you could draw a map where closely connected friends are placed near each other and distant strangers far apart. The map's distances would emerge entirely from the pattern of friendships. Nobody built a stage first. The stage appeared out of the connections. Some physicists now suspect our space-time is a map like that, with distance emerging from the pattern of quantum entanglement among the deepest bits of reality. If this is right, it flips the whole problem of quantum gravity on its head. For a century, physicists tried to make gravity quantum by taking space-time and applying quantum rules to it. But If space-time itself emerges from entanglement, then space-time was never fundamental to begin with. Gravity, being the shape of space-time, would also emerge from the deeper quantum connections. The reason gravity resisted every attempt to quantize it might be that we were starting from the wrong end, trying to quantize a thing that is already a byproduct of the quantum world. In this vision, the true foundation of reality has no space and no time. It is a web of pure quantum information, entangled with itself in intricate patterns. Out of those patterns, distance emerges. Out of distance, space emerges. Out of the way that space bends and flows, gravity emerges. And out of all of it together, the universe you see, with its stars and its distances and its falling apples, arises like a grand illusion spun from connection. These are among the boldest ideas in science, and they share one crushing weakness. The scale where all of this happens sits impossibly far below anything we can reach, which forces the hardest question of all. If the answer lives at the Planck scale, forever sealed away, how could we ever test any of it? Here lies the cruelest obstacle in the entire search. Every idea we have explored, the foam, the strings, the loops, the emergent space, all of it plays out at the Planck scale, a realm so small that reaching it directly may be forever beyond us. A theory you can never test is a theory stranded halfway between science and dream. So the question that haunts every physicist in this field is brutally simple. How could we ever check? Start by grasping just how far out of reach the Planck scale truly is. Our most powerful machine for probing the small world is the Giant Particle Collider that smashes protons together at nearly the speed of light. It is a marvel, the largest machine humans have ever built, a ring miles across buried underground, and it can probe down to distances around 100 million times smaller than an atom. That is an extraordinary achievement, but it falls short of the Planck length by an almost obscene margin. The smallest distance that machine can reach is still about 10,000 trillion times larger than the Planck length. To put that gap in perspective, the collider is as far from reaching the Planck scale as the width of a hair is, from a distance that would wrap around the Earth many times over. We are not close. We are not within sight of close. Now, imagine trying to build a collider powerful enough to reach the Planck scale directly, to slam particles together hard enough to probe that smallest distance. Physicists have estimated the size such a machine would need to be, using the same principles that guide the colliders we have. The answer is soul-crushing. A collider capable of reaching the Planck energy, built with anything like current technology, would need to be roughly the size of an entire galaxy, a ring of magnets stretching across 100,000 light-years, encircling billions of stars. No civilization could ever build such a thing. The direct approach is simply, permanently, out of the question. If the only way to test quantum gravity were to reach the Planck scale head-on, the whole field would be hopeless. A beautiful set of ideas doomed to sit forever untested, more philosophy than physics. Here is the comparison that captures the despair and the challenge. Imagine trying to read the finest print in a book, print so small that no microscope on Earth could ever resolve it, and the only microscope powerful enough would have to be larger than the solar system. You would seem utterly defeated. The words are there, real, waiting, but no tool you could ever build can bring them into focus. And yet physicists refuse to give up, because they have learned a clever lesson from the history of science. Sometimes you cannot reach a thing directly, but its faint effects leak out to scales you can reach. A tiny influence from the Planck scale, if it exists, might build up over enormous distances or accumulate over vast stretches of time until it grows large enough to notice. The trick is not to reach down to the Planck length, but to catch its whispers where they surface in the world we can measure. So the hunt is on for indirect clues, subtle fingerprints that quantum gravity might leave on things we can actually observe. And one of the most ingenious ideas turns the entire universe into a microscope, using light that has traveled across almost the whole span of the cosmos to search for the faintest trace of boiling space. If we cannot build a machine to reach the Planck scale, then physicists will use the biggest instrument in existence. The whole universe becomes the microscope. And the trick is beautifully simple. You let light travel across almost the entire cosmos and watch for the faintest sign that the boiling foam of space nudged it along the way. Here is the idea. Remember the space-time foam, the churning quantum chaos that some theories say fills space at the Planck scale. If that foam is real, it should have a tiny effect on anything passing through it, including light. As a ray of light travels through the foaming space, it might get jostled, slowed, or nudged by the churning geometry, ever so slightly. Over a short distance, the effect would be far too small to ever detect, buried beneath everything else. But light does not always travel short distances. Some light crosses the entire universe, and over billions of light years, even the tiniest nudge from the foam, repeated at every step of the journey, could add up into something just barely large enough to catch. A single grain of nudging is nothing. Billions of light years of grains, stacked one after another, might grow into a measurable trace. The vast distance acts as an amplifier, magnifying an effect too small to ever see up close. Where do you find light that has crossed almost the whole universe? From the most violent explosions in the cosmos, called gamma-ray bursts. When certain giant stars die, or when dense, dead stars collide, they release a flash of energy so ferocious that for a few seconds, it can outshine everything else in the sky combined. These flashes come from galaxies billions of light years away, and their light has been traveling toward us since before the Earth existed. It is the perfect probe, light with the longest possible journey behind it. Now here is the clever part of the test. A gamma-ray burst sends out light of many different energies all at once, in the same flash. If space were perfectly smooth, all that light, high energy and low energy alike, would travel at exactly the same speed and arrive at the same moment, having raced across the cosmos together. But if the foam is real, some theories predict it would jostle high-energy light slightly differently from low-energy light. Over billions of light years, that tiny difference would build up, and the high-energy light would arrive a little early or a little late compared to the low-energy light. So, physicists point their telescopes at these distant explosions and measure, with exquisite care, whether all the light arrives together or whether the different energies show up at slightly different times. A gap would be a fingerprint of the foam, a whisper from the Planck scale finally surfacing in something we can measure. No gap would tell us the foam is smoother than expected, or perhaps not there at all. Here is the comparison that captures the genius of it. Imagine two runners of different builds starting a race at the exact same instant. Over 100 yards, any difference in their speed is invisible. But send them running for thousands of miles across a rough, broken landscape, and even a hair's difference in how the terrain slows each one would, by the finish line, leave them arriving minutes apart. The long, rough journey turns an unmeasurable difference into an obvious one. Distant starlight is those runners, and the foam is the rough terrain. Physicists have run this test with real gamma-ray bursts, and the result they found was surprising, humbling, and one of the most important clues we have about the smallest scale of reality. Physicists aimed their telescopes at the dying screams of distant stars and waited to see whether the light would arrive scrambled by the foam. The verdict was surprising, and it delivered one of the sharpest reality checks the whole field has ever received. One measurement stood out. A space telescope caught a tremendous gamma-ray burst from a galaxy billions of light years away, so distant that the light had been traveling for more than half the current age of the universe before it reached us. Inside that flash came light of wildly different energies, including one particle of extraordinarily high energy, among the most energetic ever caught from such a burst. All of it had crossed the same enormous stretch of cosmos, through whatever foam might fill the space in between. If the foam jostled high-energy light differently from low-energy light, this was the perfect chance to catch it. The journey was long enough, the energy range was wide enough. Any tiny nudge from the Planck scale, magnified across billions of light years, should have left a gap between when the different energies arrived. Physicists measured the arrival times with enormous care and asked the crucial question: did the high-energy light lag behind or race ahead of the low-energy light? The answer was startling. All the light arrived together, essentially in lockstep, with no gap that anyone could detect. The high-energy particle showed up right alongside its low-energy companions, as if space between here and that distant explosion had been perfectly smooth the entire way. The foam, if it left any fingerprint at all, left one too faint to find even across that colossal distance. This result sent a jolt through the field, because it did something rare and precious. It ruled things out. Many of the simpler versions of the space-time foam idea predicted a gap that should have shown up in this measurement. The absence of any gap meant those simpler versions were wrong. Space, at least in the way those theories described, is smoother than they claimed. Smooth right down to scales at, or even below, the Planck length itself. The measurement pushed the roughness of space, if it exists at all, into an even tinier and more hidden corner than expected. Here is why this matters so much, and why physicists welcomed it even though it killed some of their favorite ideas. For decades, the search for quantum gravity had been almost entirely a game of pure thought, beautiful math, with no way to test it against the real world. This gamma-ray measurement was different. It was a genuine experiment that reached, however indirectly, toward the Planck scale and came back with a real answer that eliminated real theories. That is how science is supposed to work. Ideas that cannot survive contact with measurement get discarded. Picture a detective with a dozen suspects and no way to question any of them. Then a single piece of hard evidence arrives, and it clears half the suspects at once. The case is far from solved, but the field of possibilities has genuinely narrowed. That is what the exploding stars did for quantum gravity. They cleared away a batch of the simpler theories and left the survivors standing. The verdict also carried a humbling message. Whatever is happening at the smallest scale, it is even better hidden than we feared, guarding its secrets more fiercely than the boldest theories guessed. Reaching it will take cleverness beyond anything tried so far, and some physicists, refusing to be beaten, have turned away from the distant cosmos entirely. They are trying to catch quantum gravity not in exploding stars billions of light years away, but on a laboratory table, in a machine small enough to sit in a single room. While some physicists chase the Planck scale across billions of light years, others have taken a wildly different gamble. They are trying to catch quantum gravity in a single room, on a laboratory table, in an experiment small enough to hold. The idea sounds impossible, and it just might work. The trick sidesteps the whole problem of reaching the Planck scale directly. Instead of asking what space looks like at its smallest grain, these physicists ask a simpler, sharper question. Does gravity itself obey the quantum rules at all? For all our theories, nobody has ever actually seen gravity behave in a quantum way. We know gravity as the smooth, classical pull of Einstein. We know the quantum world in particles and atoms. The two have never been caught mingling in a direct experiment. If we could see gravity do something only a quantum force can do, it would prove that gravity is quantum, a massive clue on its own. Here is the ingenious plan. Take two tiny objects, small enough to obey quantum rules, yet just heavy enough to feel each other's gravity. Place them near each other. Then use the strange power of the quantum world to put each object into a blur, a state where it sits in two slightly different places at once, the way an electron smears across possibilities. This is fiendishly hard to do with an object big enough to have noticeable gravity, but physicists are inching toward it. Now comes the beautiful part. If gravity is a quantum force, then the gravitational pull between the two blurred objects would link them together in that special quantum way we met earlier, called entanglement. The two objects, tugging on each other through gravity alone, would become quantum connected, their fates woven into a single shared system. And here is the key. According to the deepest principles of physics, gravity can only create that entanglement if gravity itself is quantum, a purely classical, non-quantum force. could never forge that link. So the experiment becomes a clean test. Set up the two blurred masses, let only gravity act between them, and then check whether they came out entangled. If they did, gravity must be quantum, because nothing but a quantum force could have entangled them. If they did not, something is deeply wrong with our assumptions. Either way, we learn something profound about whether gravity plays by quantum rules, without ever having to reach the Planck scale at all. Here is the comparison that captures the elegance. Imagine you want to know whether an invisible messenger can carry secret coded letters, but you can never see the messenger directly, so instead you check the two people the messenger runs between. If those two people end up sharing a secret that only a coded letter could have delivered, you know the messenger must be able to carry codes, even though you never saw it. Gravity is the invisible messenger. The two masses are the people. Entanglement is the secret only a quantum messenger could deliver. This experiment has not yet been done. The challenge is staggering, because keeping an object heavy enough to feel gravity in a delicate quantum blur, shielded from every disturbance, sits right at the edge of what technology can do. But physicists are closing in, refining their instruments year by year, and many believe it could be achieved within a generation. It would be the first direct evidence, caught on a tabletop, that gravity is quantum. If it succeeds, it would be a turning point in the deepest quest in science, which raises the question of what winning that quest would actually give us. What would it truly mean to finally understand the smallest scale of reality? Step back from the foam and the strings and the tabletop experiments and ask what all of this is really for. What would humanity actually gain by finally cracking quantum gravity, by charting the smallest scale of reality? The prize is almost unimaginably large. It would be nothing less than a single theory to explain everything. Right now, physics is split down the middle. Gravity rules the cosmos of stars and galaxies. Quantum mechanics rules the tiny world inside atoms. The two have never been joined. A working theory of quantum gravity would finally unite them, weaving the very large and the very small into one seamless description. It would be the capstone of a quest that stretches back centuries, the dream that drove Einstein through the last 30 years of his life, the theory he chased and never caught. Physicists have a name for this ultimate goal. They call it a theory of everything. Such a theory would unlock the places our current maps abandon, the regions where we keep finding dragons. It would tell us what truly happens at the center of a black hole, in that crushed heart where Einstein's equations divide by zero. Instead of a meaningless infinity, we would find whatever real, finite, strange thing gravity does when it grows infinitely fierce. The deepest mystery of the most extreme objects in the universe would finally open to us. Even more thrilling, it would reveal the birth of the universe itself. Remember, our best theory shatters at the first instant of the Big Bang, leaving the origin of everything hidden behind broken math. A theory of quantum gravity would let us see through that wall, to understand what happened in the universe's first sliver of a moment, and perhaps to answer the oldest question anyone has ever asked. Where did it all come from? Did the universe truly begin, or did it bounce out of something before? Was our cosmos alone, or one of countless others? Beyond the grand mysteries, a theory of everything might reshape how we understand reality at the most basic level. If space and time really do emerge from something deeper, from a web of pure quantum information, then we would learn that the world we move through, the distances we cross, the moments we live, are all woven from a hidden fabric of connection. We would understand not just how the universe behaves, but what it is made of at the very root. Here is a comparison to feel the scale of the prize. Imagine humanity has spent centuries with two separate maps of the world, one showing only the land and one showing only the sea. And the two maps use different scales and refuse to line up along the coastlines. You could navigate the land or navigate the sea, but never plan a single journey across both. A theory of quantum gravity would be the first map to show land and sea together in one consistent picture, letting us finally chart voyages across the whole world of reality, coast to coast, with no seam down the middle. History shows that when physics unifies two great ideas, the consequences ripple out for generations in ways nobody predicted. Uniting electricity and magnetism gave us the electric age. Uniting space and time gave us the satellites that guide us. Nobody can foresee what uniting gravity and the quantum world would unleash. But if the past is any guide, it would transform our understanding and our technology in ways we cannot yet dream. That is the reward waiting at the bottom of reality. And it leaves us with one final question. After this whole journey to the smallest scale, where does the search actually stand today, and why does it matter to you? We have fallen all the way to the bottom of reality and back. So where does the search actually stand today? And why should any of this matter to you, standing on the smooth-seeming ground of an ordinary world? Here is the honest state of things. Nobody has solved quantum gravity. The theory that unites Einstein's smooth space-time with the jittery quantum world does not yet exist in finished form. What exists is a handful of brilliant, unproven candidates, each capturing a piece of the puzzle. String theory offers vibrating threads and hidden dimensions, and gives us gravity for free, but demands a universe far stranger than we can test. Loop quantum gravity weaves space from smallest possible grains and tames the infinities, but struggles to connect back to the familiar world. The newest ideas suggest space and time themselves emerge from quantum entanglement, a vision so radical it is still being born. Each is a partial map, none is the whole territory, and the experiments are only beginning to bite. The distant exploding stars have already ruled out the simplest pictures of boiling space, showing that reality guards its smallest scale even more fiercely than we guessed. The tabletop experiments creep closer each year to catching gravity in a quantum act for the first time. The search is no longer pure thought. It has become a real hunt, with real clues arriving, narrowing the field of possibilities one measurement at a time. Why does this distant, tiny frontier matter to you? Because the answer sits underneath everything. The ground beneath your feet, the light reaching your eyes, the atoms that make up your body, the flow of time carrying you through your life. All of it rests on the deepest laws of reality, the laws we are trying to read at the smallest scale. To understand quantum gravity would be to understand what the world is truly made of at the level below atoms, below particles, below space and time themselves. There is something profound in the fact that a creature made of atoms, standing on one small planet, can reason its way down to the Planck length, a distance so small it makes an atom look as vast as the universe, and ask what happens there. We cannot see that scale. We may never build a machine to reach it, and yet, using nothing but mathematics, careful thought, and the faint whispers of light from dying stars, we have mapped the edge of where our knowledge ends and charted the strange country that must lie beyond. Here is the comparison to carry with you. For most of history, humans stood on the shore of the known world and stared out at an ocean they could not cross, filling the blank spaces on their maps with monsters. Then, one voyage at a time, they crossed it, and the monsters became coastlines. The smallest scale of reality is that ocean now. Quantum gravity is the far shore. We are still on the beach, building better ships, reading the currents, catching the first faint signs of what waits across the water. But the voyage has begun, and the greatest minds of our age have set their course. Gravity might truly break down at the smallest scale, our finest theories dissolving into foam and infinity. Yet that breakdown is the most exciting signpost in all of science, an arrow pointing straight at the deepest secret the universe still keeps. Somewhere below the atoms, below the particles, at the very floor of existence, the answer is waiting. And one day, someone will reach it,